Okay.
When should we start?
Yeah, Lipeng.
When should we start, Yusi?
No, it's good. Yeah.
When should we start?
No, it's good.
No, it's good.
Yeah.
Good. Okay. Okay. Hello, everyone. Welcome to the virtual conference on reinforcement learning for real life. Sorry, my video is not on because my Wi-Fi is not good at the moment. So I'll turn my video off and just talk. The goal of the conference is to discuss key research problems when applied RL to the real life, as well as to share successes and lessons in this process. The conference has two runs. The first Atlantic run focused on healthcare applications, while the current Pacific run will cover other application domains as well. We'll start with a panel discussion where we have a group of experts from both academia and industry to share their stories, insights, and perspectives. If you have any question about RL for the panel, please feel free to submit it on Chisider or at the channel of Slack. And after the panel, we'll have a poster session. It's amazing to see a long list of interesting works. I hope you enjoy the poster session as much as I did in the Atlantic run earlier. And then after the conference, the panel discussion will be available on YouTube. All the information, including links, can be found on the conference website. So these are all the technical details. And without further ado, let's start a panel session. We're honored to have these experts and thought leaders to join us. The first is Dr. Ed Chi. Ed is a principal scientist at Google, leading several machine learning research teams, focusing on neural modeling, including machine learning, reinforcement learning, and recommender systems in Google Brain. He has delivered significant improvements for YouTube, News, Ads, Google Play, Store at Google. He has also been widely recognized in the research community, including the 20-year Test of Time Award for Research in Information Visualization. Our next speaker is Professor Chelsea Finn. Chelsea is an assistant professor in computer science and electrical engineering at Stanford. She works on reinforcement learning and robotics, among other topics, and has won many awards. Just to mention a few, she got the ACM Doctoral Dissertation Award and the MIT Technology Review 35 Under 35 Award. Our third panelist is Dr. Jason Gauchi. Jason is a software engineer manager at Facebook AI. He has done many exciting works on deep learning. Related to the conference is that he's leading the reagent team that uses reinforcement learning to do automatic marketing for billions of people. The work looks really interesting and is open source. And finally, I would like to thank Professor Peter Stone to moderate the panel discussion. Peter is the David Bruton Junior Centennial Professor of Computer Science at the University of Texas at Austin. He's also an Alfred Sloan Research Fellow and AAAI Fellow. Peter has done extensive work applying RL to very challenging problems like robot soccer. So Peter, this is yours. Thanks.
All right, thank you very much, Li Hong, for the introductions and for putting the panel together, and all the organizers. It was a great panel in the first session, and we'll see what we can do to follow up on that in this session. We've got a great group of people, and I saw some very interesting questions. So I'll try to watch if there are new questions posted. But let me just start to sort of break the ice and get so that we're all sort of talking about the same thing. What when we say real life reinforcement learning, what does that mean to you? So all three of the panelists, what do you think are the most promising applications in the real world that reinforcement learning is appropriate for? And I guess beyond the healthcare that was the focus of the morning. And why don't we go? On my screen, you're in the order of Ed, then Chelsea, and then Jason. So let's start that way, and then next time we can mix it up.
All right, so I guess I've been volunteered to be first. Obviously, since I work in recommender systems, there was a couple of different reasons why we're very interested in using reinforcement learning. I think the spirit of reinforcement learning at its core is really about planning. And much of recommendation systems actually have been built essentially is to design basically for the next transaction or the next sort of item that you might be interested in typically. And so what that means is that recommender systems actually for a very long time is not truly a planning system, right? There's planning in the sense that it remembers what happened in the past and maybe it might be able to play back those things. But it doesn't really plan for things like, for example, if you wanted to learn swimming and you're going from beginner to advanced, what are the set of videos or articles should you read about so that you would essentially upskill your swimming abilities, or it could be any other learning activity that your kids. My daughter, for example, is really into Scratch programming right now. One would imagine that a good recommender system would be able to essentially create a true learning curriculum for her over time. And so that was the really sort of the inspirational mission that we started using reinforcement learning in recommender systems. But it turned out to be obviously quite more difficult than we had imagined several years ago. So, and I guess we'll probably have more discussions about that.
Okay, great. So Chelsea.
Yeah, so I work a lot in robotics and reinforcement learning for robotics. I think it's a very, very natural application area for reinforcement learning, and one where there's an extremely tight feedback loop between the decisions that the robot makes and the next state that it sees in the world. And I think that it's I guess in some ways when you deal with real robots, you're already dealing with the real world, but in some ways you're actually not yet dealing with the real world if your robot is in a lab environment. And I'm quite interested in how we might push robots outside of the lab into much more real environments, like the environments that humans live in and interact in, or in other sorts of environments as well. So like factories, for example. So I think that a lot of robotics really faces a lot of different challenges that are unique to problems in comparison to ones that are more in simulation or more in games and so forth. So I think that a lot of the things that even in the lab, a lot of the lessons that we learn there are valuable for more real world reinforcement learning systems, but also many more challenges to come in terms of actually putting these in the real world. One other thing I'll note outside of robotics is I think that really any machine learning system that's going to be interacting with a user at some point is probably actually going to have some sort of feedback with that user. And it could make sense to not we often treat these sort of problems as supervised learning problems when we're labeling images or translating language. And if there's a person on the other end and that person is using your system repeatedly, then there may actually be benefit at some point to treating it as a reinforcement learning problem.
Okay, good. And Jason.
Hey everyone, thanks for joining us, everyone. Yeah, I mean, Ed and Chelsea, really hit the nail on the head. I mean, for me, RL in the real world is ultimately about making decisions, and you most of the time when you're doing machine learning, the goal is to make some kind of a decision. I mean, imagine you're doing some classifier to classify dogs versus cats, some image classifier. What's the goal? Like, if the goal is an app that would be cute, like to show your kids, then maybe you don't have to be that confident. You could just pick the highest probability. But if the goal is something like, let's say, cancer screening, then you're going to have a totally different strategy for that problem, even though on the supervised side, the signal processing part of it is the same. And so anytime anyone does machine learning, or maybe even more broadly, anytime we build anything at all, it's in service of some end user, right? And so we're going to be making decisions to try to make that to try to provide utility to that person, right? And so I feel like we've we've created a lot of low-hanging fruit as an industry by not sort of mechanizing the sort of decision-making process, and by hand coding a lot of these policies, as Ed kind of pointed out. There's a lot of supervised learning, and then there's this hand-coded policy. And so I think for me, it's moving the entire industry from hand coding policies and really complicated supervised learning over to I guess hand coding utility functions, which is a little bit closer to answering the real philosophical economical question that we care about, and then letting the machines do the signal processing and then do the decision making. And your reinforcement learning is the most broad, most powerful technique sort of under this umbrella to make those kind of decisions.
So let me push you on that a little bit, Jason. So Ed and Chelsea gave sort of specific domains, recommender systems, robotics. What's your favorite application that you've worked on yourself, or what as a real life application of this general paradigm of tuning utility programming utility functions?
Yeah, it's a good question. I mean, I think so. Similar to Ed, I've been in the recommender system space for a long time. Before that, I was doing flight control systems, and guidance and navigation control systems for drones and things along those lines. I mean, I think if you take it to the limit, everything that makes a decision should be disrupted by this technology. And so things like healthcare, to me personally, are really exciting. I think things in robotics are extremely exciting, especially when you look at manufacturing robotics. These aren't areas that I've tackled myself, but I think that there's huge opportunity, and anyone who's building software for anything could look at this and figure out how it can work in their field.
Great. So so Ed and Chelsea, Jason both gave some things he has worked on, flight control systems and recommender systems, and then reached a little further and said, okay, here's some great applications that I haven't worked on yet, but that I'd like to in the future, healthcare and manufacturing. So what first Chelsea and then Ed, what do you see as the something you haven't worked on yet, but that you see as an exciting application that you'd like to move to in the future for RL?
Yeah, so I guess a couple of things. I've primarily worked on robotic manipulation, so arms, figuring out how to manipulate objects and so forth. I'm excited to move more towards mobile robots at some point, essentially robots that can move around, that have wheels. I think that by doing so, they can experience much more about the world, and we can hope to actually get much broader generalization by nature of having much broader data sets. And also, I guess, so that's one thing that's still sort of in my area of expertise. And then one thing that is less in my expertise, but also seems like a really nice test bed for, and actually application area for reinforcement learning, is areas like computer systems, where you need to optimize something about how the computer is operating, or how low-level software is operating. It seems like that's an area where it may be possible to collect a lot of data potentially, and also an area that could have tremendous impact by making computers work better for us, essentially.
Yeah, and there's a history of even 20 or 30 years ago, there was sort of beginnings of beginning research on using machine learning methods, usually supervised learning, like for branch prediction in computer architecture. And some of those things are taking off now, and definitely there's a community starting to get interested in RL for sort of the interiors of computer systems. Though you have to watch the time constants when you're dealing with hardware and caches and things like that. Ed, what about you? What's another topic you'd love to move to in the future that you haven't worked on in the past?
Well, so I don't know about the future, but certainly ones that we're already working on that hasn't quite worked yet. And kind of to riff on Chelsea's point there, we have been, some of you may know that I was recently involved in some learned data structure papers, so learned indice papers. So there's definitely a lot of hope that RL might be applied in database systems. There have been a couple of papers by my co-author, Tim Kraska, on these topics. So for example, query optimizers in database systems, could we use RL to optimize them. But then beyond that, my team at Google have also recently been working on looking at using RL for optimizing compilers. I think maybe the point really to make is that sort of inspired by chess playing and the Go playing work by DeepMind, areas where there are simulators that are widely available, or at least the label data, you can sort of virtually play the game and get label data. Those kinds of application areas, like compilation, you just have to compile to find out how big the binary is or how fast the binary is going to run. These are the kind of areas where I think it's really ripe for RL applications. And then I might also add that even though Jason and I both talked about recommender systems, it turns out that, of course, within recommender systems, they're connected to many other systems where RL could be applied. So, for example, recommender systems often either maybe send email or send notifications. So there's a notification system inside of them, and notification systems might be controlled by RL algorithms, classifiers, for example, whether it's for trust and safety or other forms of content control type of things in recommender systems are also potential areas for RL algorithms to shine. So those are the kinds of things that I think are really within the next, maybe 1 to 2 years, or we're already working on them, and we believe that it will become successful in 1 to 2 year time frame.
Yeah, I mean, if I could jump in, another area that I'm really excited about is market optimization. So I mean, look at look at Amazon, for example. Like if I go on Amazon and I type batteries, I'm actually going to get the Amazon brand batteries first, right? And if I go to Alexa and say buy batteries, she's going to buy the Amazon brand batteries, right? And so that's probably best for me, but it kind of starves a lot of the producers. Like it starves like the the battery producers, right? And so you could think of this as a market where you're only optimizing for one side, which is the consumer, right? I mean, imagine if at a conference, everyone goes on Yelp and types pizza, and Yelp sends all of them to the same pizza place, right? So we want to optimize for both sides of this market. And I think that's something, I mean, look at Uber, right? I mean, you have people who want to get to places quickly, but then you also have drivers who want to save money on gas and economize, right? And so I think this like bipartite optimization, bipartite decision making is another area that's going to get disrupted. And I think that's huge opportunity because there's just tons of marketplaces out there. And so that's something that we're working on, and hopefully you'll have some results soon.
Great. So one of the questions from one of the audience members brings up an application that none of you mentioned, but curious if any of you have thoughts on it. So the question was, what's your opinion on reinforcement learning for science? For example, drug discovery or optimal design of biological sequences, physics. What do any of you have anything to say about the uses of RL as sort of a tool for scientific advances?
I might be able to start because I have a team in Cambridge right now led by a guy named Dee Scully of the technical debt in RL, in ML thing, who's been working in that area. In sequence design in particular, genetic sequence or protein sequence or what have you in that space, RL could be thought of as a family of algorithm for doing sequence decoding. So those problems typically have a sequence encoding part and a sequence decoding part, and the decoding could be controlled by an RL policy. But generally, pointer network, intentional methods, as well as graphical neural network approaches are pretty competitive compared to sort of RL algorithms. Where they might shine a little bit is in connection to other experiences that we recently have had at Google. So for example, the chip design problem is a floor planning problem. And that's basically a geometric sort of bin filling 2D, 3D-ish, not quite 3D, but 2.5D kind of planning problem, layout problem. There's some sense that some of the biological sequence decoding problems and that problem have some similarity. But the bio one obviously is even more complicated because you have to understand the chemistry. And the chemistry is, it's both physical, or you could try to use a neural net to sort of learn the patterns or rules or whatever. But there are definitely some success there. If people are interested in that space, for example, you can look up a project called Nosebrain, where we're trying to predict how chemical molecules are actually going to smell like just by looking at the sequence. That kind of thing have been reasonably successful in our research groups.
Good. Chelsea or Jason, anything you want to add on that topic?
One thing that I can add briefly is just, I don't know if I think that machine learning in these sorts of contexts makes a lot of sense. I'm not sure if reinforcement learning in particular is like the exact method to start with for these kinds of problems. But I will add that I know that there's, well, with the caveat that this is not in my area of expertise, there is work on using meta learning for some of these kinds of problems, like drug discovery, for example, where you may have kind of a little bit of data for a lot of different molecules or a lot of different potential drugs, and in terms of a little bit of data, their interactions, and if you can leverage that data with a meta learning algorithm to quickly kind of predict the sorts of interactions that you might get for a new drug or a new molecule, that's kind of exactly within the lines of a meta learning problem statement.
Good. Yeah, and I guess I can throw in also on that question. I've had a collaboration with a colleague of mine, Mike Mock, who is a neuroscientist who studies the cerebellum, and we've had some very interesting exchanges looking at the kinds of problems his cerebellum simulator, which is designed to be biologically plausible, the kind of problems that it can solve compared to the kinds of problems that reinforcement learning algorithms can solve. And you know, and trying to understand to what extent is the cerebellum doing reinforcement learning versus supervised learning versus model predictive control. And this is something that I think there are a lot of potential connections between neuroscience, certainly, and reinforcement learning. There's a chapter in the most recent edition of the Sutton and Bartow book that look at those connections as well. So that's also an obvious place to look. Let me move on to another question. So Ed, you sort of offhand said at the end of the first question, you said that you've been working on recommender systems and that it ended up being more difficult than you thought. And I think this is a common something that we all come across when I teach my class in reinforcement learning. Students often say, "Oh, reinforcement learning worked in Grid World and Mountain Car. I have this problem. It should be easy to apply." And then we often find that it's more difficult than they thought. And so I guess what are the examples that you've come across? What are the specific challenges? Chelsea in robotics and user interaction, and Jason in flight control systems, and Ed in recommender systems. In what ways was doing reinforcement learning in these kinds of settings more difficult than you thought, and how did you address them? Let's start with Chelsea this time. We'll go Chelsea, then Jason, then Ed.
Yeah, I think that, in general, I think that so many things about robotics are hard. I think that it's so easy to underestimate how hard it is, simply partially because manipulating objects is just so intuitive and basic for us that it seems like it should be so intuitive and basic for robots as well. But of course it's not, and robots don't don't have the experience that we humans have in many ways. So I think that's one reason that makes it easy to overestimate. And I still remember when I took my first robotics course, I thought it would be easy to kind of plug in existing algorithms and get a robot to do something. And always the system does something that is a little bit different than what you might expect. I think that there are a lot of challenges when moving from simulation to the real world that you may not expect. Things like not being able to reset the environment at the beginning of every episode without a human literally doing that. You can sit there and help the robot reset the environment every time, but it gets a little tedious after a while. Things like reward function design, which I think is in general a problem. What sort of reward function do you give to the agent? designing the reward function may be harder than the problem itself. Like if you want to pour water from one cup to another, the reward function would need to be able to recognize liquid essentially. What else? Those are two examples, I guess. Also handling perception is a really big part of the problem as well, and being able to figure out how to perceive the world and see, which in many ways is a whole nother subfield of AI in itself.
Yeah, I know. The first time that one of the first applications I did reinforcement learning in robotics was learning a quadruped robot learning to walk. And I think one of the biggest reasons it made a splash when it did was that we didn't have to reset the robot. It could just walk back and forth itself. And that was something that sort of made a big difference, because that's often not the case in robotics applications. Jason, what about you?
Yeah, it's interesting. I mean, I think there's some, in the beginning, there was some, going to recommender systems folks and you're pitching kind of decision making and reinforcement learning. There's just a lot of knowledge building to do in the beginning. I mean, people would say, how is this going to improve the normalized entropy of my supervised model? And so we have to kind of get down to, like, what is actually making the decision? And what we found is what's actually making a decision is usually something very simple, where you've taken these supervised models and you've done a weighted linear sum of them. And the weights were learned through some black box optimization. And then we said, aha, that's the thing we're competing with, not this gigantic supervised model. So first was sort of like narrowing down, like, okay, what specifically is the area? After that, I think one of the biggest challenges is doing, batch decision making, doing batch policy optimization. It's actually really, really hard. Like, I'll give an example. Imagine you're doing a DQN, but this isn't like an OpenAI gym where you can just keep rolling out the policy in real time. You're going to train on, a day's worth of OpenAI gym, and then you'll push out a new policy for tomorrow, right? If I add an action in the data set, I don't have to actually take that action, but I just say there's another action you've never seen before. The DQN will pick that action some of the time. And because it's not part of the loss, that action will cause all the other Q values to be wrong. So you can see how, like, just adding a dummy action to the data set breaks everything. And so what we found is although there's a whole bunch of theoretical guarantees, when you get down to brass tacks and noisy data sets and partially observable situations, which is the real world is full of these things, you really have to do a lot more than what comes out of the box to actually do true off policy in a safe way, and to deploy something where you're not on call, you're not getting a page at 4 a.m. saying, oh, the Bellman equation isn't working, right? Like, to do this in a safe, rigorous, dependable way, but still have kind of exploration and policy optimization. That ended up being way harder than we thought. I mean, it took years, and we still have a long way to go.
It's almost surely not that the Bellman equation isn't working. It's got to be something else. The Bellman equation always works. Ed, what about you?
I'm so glad that the Bellman equation came up, because I was just planning out my answer, and that was going to be in the middle of it. So that was perfect. So the advantage of going third here is I can build on the previous two answers. I love Chelsea's point about reward shaping, and that was one reason why we were very interested in using RL for recommender systems, because to some extent, in supervised learning, we have spent a lot of time already figuring out what goals we care about, and the market kinds of problems that Jason was talking about earlier. We kind of have some ideas about the kind of efficient markets that we want in between creators and viewers or consumers or whatnot. And there were a lot of good signs, right? We were thinking that there in recommender systems, typically we have a lot of data. We can run live experiments. AlphaGo has showed us that large action spaces is not as intractable as maybe we thought, and so robotics typically have a lot of continuous control problems in discrete action spaces, like in recommender systems. Seems like maybe it's not as bad, when we first started. And so given that we have all read these textbooks or maybe watched the lectures, our thought was Q-learning plus Bellman updates, try it out. We have lots of data, run experiments and see what happens. What we actually ended up finding out, and to some extent, I think in the stream here, we're starting to get a related question, which is, what is the safety when we need to generalize to unseen situations? Well, what we found out as we try to apply these algorithms is that Q-learning is not at all reliable. In fact, the Q value estimates that we typically get in recommender systems, even despite the fact that we have a lot of data, despite the fact that we have a reasonably good understanding of reward, even proxy reward or partial rewards, is that the Q values are actually not reliable and have huge amounts of variance. And part of it is because the trajectories, the combinatoric of the trajectory is humongous. So even though the action spaces may be, millions or double-digit millions, but the combinatoric combination going forward actually turned out to be a lot more difficult than we thought to control the variance. And so the name of the game turned out to be completely about how do you control the variance, and algorithm is not nearly as important. In particular, a lot of our energy went into counterfactual learning, just really understanding what data points in our data set gives us counterfactual, essentially understanding of in what circumstances what data is more reliable and in what circumstances which data points are not reliable or are not going to lead to good outcomes. So I think at the conceptual level, in the end, those are the kind of problems that we really had to solve in order to be successful.
Great. So that's a great segue. Let's go in that direction. It's the most popular question on the website, and also there's been some in the YouTube stream, as you said, really about using reinforcement learning in safety, and its relationship to safety. And I ask this question, sort of differentiate between two types of safety. There's safety from the perspective of controlling the variance, like you're saying, and there's of course methods like distributional RL, robust RL that think not just about the expected value, but think about the whole distribution of values. And then there's safety from a perspective of, don't crash while you're learning, don't drive off a cliff while you're, learning. And so, from both of these perspectives, what have been your experiences? How, I guess it was phrased on the website as, your experiences using it for safety critical missions like autonomous cars. How can we address these two types of safety? How have you addressed it in your applications? Ed, you already said something like that. So let's start with Jason and Chelsea and then come back to Ed. Jason, go ahead.
Sure. Yeah. So, one thing Ed touched on, which I can echo, is this idea that counterfactual learning, counterfactual evaluation is extremely, extremely important. What we typically do is, we'll log not only what happened, but we'll log what the alternatives were. So, for example, if we're doing in marketing, we're doing some email distribution filtering. We'll log even when we decide not to send the email, we'll log that. We'll also have exploration, and we'll log the propensity. Like we'll log the probability. So if we're doing let's say epsilon greedy, and this was an epsilon action, it was an explorative action, we'll make note of that. And then we use all of this information to do a lot of offline evaluation. And one of the things actually we're working with the sort of fundamental research department to actually spin off our offline evaluation into a separate project, because we feel that, to be honest, it's actually more important than the reinforcement learning library because it's more broad. I mean, anyone who's making any kind of decision can use offline evaluation to roll out things safely. I mean, even if you're doing collaborative filtering, you could still do offline evaluation to know if tomorrow's collaborative filtering model is unsafe for some reason. So that's more on the sort of like safety in terms of, guarantees that you can give yourself when you roll out models. I think when you get to things like making sure the policy is sound, that's where you start getting into more of like a PPO, TRPO type idea. And for discrete actions, there's things you can do that are along those lines. Basically, you can look at the divergence of your policy from your data set, and measure that, and maybe do some early stopping, or maybe you don't roll out this policy. You send an email with a warning saying, there's huge divergence here. It could be that you found some amazing new way to drive from San Francisco to Dallas in 4 hours, but probably you didn't. Probably there's an issue, and we should look into that. So yeah, I think measuring sort of the divergence and understanding that there's two optimization loops going on. Like, you're training this model, but then you're also adapting you're also having this back and forth between your environment. And so in the same way as you wouldn't set your learning rate to 1.0, you also wouldn't go all in on DQN to infinity and then roll out that policy. You would kind of take baby steps. And so I think those are two things that really helped us out.
Good. Chelsea, how about you?
Yeah, so I have a few thoughts here, some of which has already been mentioned to some degree, but I think that in many of the kind of classical reinforcement learning benchmarks that the machine learning community uses, like Atari games, like the half cheetah, the gym environments and so forth, I think that so often we think about starting completely from scratch with like a completely random policy or random exploration. And I think that in basically all real world applications, that's not what it's going to look like. If you're actually going to be in the real world running reinforcement learning, you're going to be starting from some data. And like in robotics, for example, if you imagine putting a robot in like a kitchen and saying, okay, start learning, if it starts with random exploration, it's not going to get anywhere at all. So you're going to need to start with some data that does something somewhat reasonable, whether it be demonstrations, whether it be examples of humans doing things, and so forth. So I think that moving away from this paradigm of learning completely from scratch and thinking about how we can leverage data sets, in a particular offline data sets, the batch RL setting, thinking about how we can integrate that data will be really critical for deploying systems and also for deploying systems safely, because that if for autonomous driving, for example, if you have a lot of data of humans driving, if you can learn from that data effectively, then you shouldn't have to explore quite as much. My second thought here is that I think that when thinking about safety, it's very natural to think about, well, maybe I can just try to manually construct the sort of situations that I think the policy might get into and constrain it in a manual way. Think about all the things that might fail and try to prevent those things. This is actually a pretty common approach in robotics to safety, where you just constrain the actions and the kind of how fast the robot will go and the where it will go and so forth. And I think that this sort of approach, while it will kind of get us some of the way, I think that ultimately it's not going to get us all the way in terms of real world applications. And this is because we know all of the kind of limitations of manually putting things in, and that's why we're using machine learning in the first place. So I think that ultimately we're going to need to have algorithms that can learn notions of safety and learn what actions lead to unsafe outcomes and incorporate this, what was learned from these data sets into the algorithm, so that kind of akin to how humans learn by doing unsafe things, the robots and other systems can also learn from mistakes made in the past.
Great. Ed, how about you? Anything more you want to say? You already talked a bunch about safety, but anything more you want to add based on Chelsea and Jason's responses?
Yeah, no, I think especially Chelsea's point, I wanted to add to it a little bit. One, the uniqueness about recommender systems is, to some extent, it is by nature already a human in the loop system, basically. And when I think about how to apply RL systems, is that it is critically important in designing these practical systems for you to understand essentially what's when we talk about batch RL, what's the time interval between the next time the model is going to basically refresh. So if you think about the planning problem that you're doing in applying RL, you're only planning basically as far as to the next time that the model is essentially refreshed for the user. And so you have to think about how far you're planning ahead and the safety problem therefore is connected to, because the variance, if you have to plan for a whole week, for example, is very different. Now, I mean, imagine the analogy that I give to people a lot on this is, imagine that you're going on, well, not in these days with the virus and everything, but imagine that you're going on a trip for one day and you can look at the forecast and decide what to bring with you, versus going for a month or 6 months. Now, the amount of things that you bring are a lot more, because you have to plan for a lot more various different kinds of weather. It's the same thing in recommender systems. The longer the plan, the more they have to deal with more variety of different possibilities. And so this is why I think a lot of the recent research on reliable ML and also uncertainty estimation and its connection to RL and ML in general has been really great. Obviously there's been a lot of exploration on sort of KL divergence or entropy regularization technique. Basically, there are various techniques for not moving away from the training data too much, right? And that's one way in which you can control for safety, is basically you say, I'm not going to be planning for more than 6 hours or 24 hours, and I'm not going to deviate from my training data by this much. And that allows you to really kind of bring that safety envelope in and have some confidence that your system is going to do reasonably okay.
Good. So actually, let me circle back, and expand on something you said, Chelsea. So as you said, in robotics, you often don't want to learn from scratch. And I know the example of the kitchen, Leslie Cabling talks about a lot as well. You don't want the robot to learn in your kitchen. You want it to come ready to just learn some things, and do most of the learning beforehand in the factory. And we do in robotics use a lot of learning from demonstration, trying to build in knowledge one way or another. But of course, the tension is then you're also building in biases, and there's sort of the examples from AlphaGo that people point to, where when you were learning from humans, then it sort of biased things. When it went to AlphaZero, then it was able to do better. And so some ways it's necessary if you need to be sample efficient, but some people would look at it as a necessary evil. So how do we, when you are trying to build in knowledge, how do you do that in a way that also leaves open the possibility of exploring new things that people wouldn't have found, or that is far away from the training data, right? You want to be safe. For safety, you want to stay close to the training data, but for innovation and surprise and optimization, you want to let the freedom go in. So how do you manage that tension? Chelsea, if you want to start, since it's a follow-up on your comment.
Yeah, I think that there's definitely some tension there. I think it also depends on your goals. If your goal is to get a robot that can do the sorts of things that humans can do, but in a way that is more reliable, that doesn't text while driving, that doesn't like get tired or so forth, then that bias may not be that bad. I think that if you are running some sort of reinforcement learning, then rather than imitation learning, for example, then you do have the ability to go beyond the capabilities of what's in the data. So that's always something good. And in the AlphaGo, for example, I think the data that they trained on, they were able to get better far better than what the data that was trained on using reinforcement learning. Although, of course, it wasn't hitting quite the upper limit of what it was able to accomplish. So in some ways, I guess, I think that robotics is such a hard problem that I'd love to even get to the kind of the equivalent of AlphaGo in this setting as kind of a first step. And maybe from there, we can think about doing even better.
Okay, Ed or Jason, anything you want to add on this sort of tension between building in or importing knowledge versus allowing freedom to explore?
Yeah, I can jump in. So I think so one thing that's really interesting is when you see the river change directions, right? And so just in general, when you see this phenomenon, it's interesting just in life. And so one of the places where the river has changed directions is we started off with, before deep learning, we were doing image processing. We did sort of SVD, and then we created some latent space, and then we would do a linear model like SVM or something like that. And the idea there is you can't just do SVM on pixels, right? And then we went deep learning, which went straight from pixels to some supervised signal. So we trained great ImageNet models, right? And then now we're using sort of transfer learning. And so it's that the river has kind of come back the other way, where someone else, a Google, a Facebook, has trained this enormous BERT model for us. And then we just use it. And maybe, the weights change slightly, but we're just willing to tolerate that bias because this enormous self-supervised system has been pre-trained for us, right? And I feel like RL, we don't yet have our sort of BERT moment, right? I mean, I would like the kitchen robot in your example to have this 40 gigabyte self-supervised pre-trained model, and maybe it's a forward model in physics, or it's maybe a forward model in physics that's specific to like a way a spatula bends or something, right? But you can imagine in the future robots coming with these giant models, and then sort of an intermediary applying the robot to a specific task using that model, and then maybe a third stage when it gets to your house, right? And so, yeah, I think all of us are kind of waiting for that moment. And when I see the OpenAI results in robotics, they're all kind of end to end. And so, I don't think we've seen it yet, but I do think that's sort of where the whole industry is kind of going. And I think when we get there, it could be pretty exciting. There could be like a Cambrian explosion, similar to when people were sort of hacking on the Roomba, right?
Maybe the way to think about exploration, particularly when it applies to recommendation systems, is really whenever recommenders really deliver a magical experience that you didn't expect. And there's been, I would say, a natural tension that's happening in there, which is that, on the one hand, people kind of sort of say their expectation is that they understand what the recommender system is doing. Why they're recommending this to me. But then at the same time, they're expecting magical experiences because they, don't want to get the same thing over and over again, basically. I think the expectation, I'm old to remember when recommender systems weren't around and search engines were around. And they were originally very magical experiences. There was a time when search engines like Archie actually took multiple minutes to return results. And now our expectation is completely different. So I think the challenge in applying RL, in particularly in recommender system, thinking about exploration, is how can we really kind of magical experience? And so it goes back to my original point, is the day when we can use RL to really deliver a curriculum, that would be the point where we would say, oh, yeah, we've succeeded. It really is magical and exploratory.
Good. So let me shift gears a little bit. We've had a couple of questions both on the website and in the YouTube stream on benchmarks. And so, a question is, what are there, one was phrased, should we put more efforts into developing benchmarks closer to real life problems? Another version was, can we train a reinforcement learning policy only based on a fixed data set? From your perspective, is when we're talking about reinforcement learning in the real world, or for real life, are those inherently one-off specific applications where you're going to be working on the details and it's it doesn't really is not conducive to benchmarks, or are there ways that we can develop benchmarks that are different from the Mujokus and those kinds of things, and pole balancing and grid worlds, that allow us to study the problems that are the bigger challenges when you try to apply things? How do we do that? Any one of you. I'm not going to pick the order this time.
All right, I'll take a crack at it.
Go ahead, Jay.
So, okay, one thing I would dismiss the idea of like one-shot RL. So you have a training data set and your RL policy is optimal. Trust me, we've tried that, and it hallucinates. For most complicated problems in the real world, it tends to hallucinate. And so I would go into it thinking in terms of this feedback loop, as Chelsea mentioned, this kind of closed loop, right? I mean, ultimately, that's what contextual bandits, reinforcement learning, Bayes opt, like that's what these things are good at, is dealing is in closing the loop, right? That's where the advantage is. And so if you have an open loop, then there might be other techniques that would be better, like collaborative filtering, right? In terms of the benchmarks, it's a really interesting question. I'm sure Ed knows a lot more about RecSim. We've recently started looking at RecSim, and it seems pretty cool and pretty adaptable. I think the benchmarks will continue. I mean, there's a lot of stock market trading data, and you can look at decisions the Fed Reserve made and things like that, and so you can there's tons of records of decisions that were made. But in general, I think that this is actually one of the most exciting areas. And I think it's because it's so contextual and it's so personalized. But I mean, we're seeing a lot of these other areas like CV and speech, translation becoming almost like more commoditized. I mean, I don't see why Facebook's, English to Spanish translation should be any different than Google's, right? But in our case, in decision making, it's highly contextual. And so, I think there's always going to be good work on benchmarks so that we can continue to advance the field. But I wouldn't expect benchmarks to give you any more advantage when you go to solve your problem, because it's going to be very different.
I'll go next and say that I think one thing that we can think about this benchmark question is by looking at in the NLP space a little bit. I think someone, I forget who it was that brought this up, that what's our BERT moment or whatever it is in RL. Actually, I'm a little bit discouraged by this what's going on in NLP right now, personally, for the following reasons. There were some papers recently talking about compositional generalization in NLP. And so basically, they're about a set of sort of NLP semantic kind of reasoning problems. So, you can imagine easily constructing from text, reasoning about logical reasoning or something along that line. And what we're kind of finding out, actually, BERT, these kind of recent advances in NLP, BERT models, they're actually really good memorization models, but they're actually really poor at compositional generalization. Basic reasoning is still really not solved in NLP. So I think this is an awesome question, because I think the question wasn't just benchmarks, but what could be RL benchmarks that measure true generalization performance? We need something like the challenge data sets that have come out. I think they're from New York on the NLP side, and looking at these compositional generality problems and saying like, look, BERT is actually not performing well. I think actually scored 0, if I remember correctly, on some of the paper I read. They're just not able to do any reasoning at all. And so I don't think RL algorithm necessarily needs to be able to do reasoning. So counterfactual learning might be a form of that. But this is an awesome question, because the Majukus and whatever that we have, the carpools, they don't really measure anything about generalization. And our hope has always been that neural networks is really going to generalize to new situations. So far, my personal opinion is that it's really just a very sophisticated counting machine, a compression one, but it's really just a counting machine.
So perhaps another take on this is I think that in benchmarks, a lot of times kind of the existing benchmarks people put out in an environment that has like a reward function, an action space, and so forth. And I think we actually need to move more towards NLP in the sense that I think that we shouldn't just be releasing an environment, but also a data set, an initial batch of data that such that you can kind of start to study batch RL settings, such that you can start to study batch RL plus some fine tuning, or kind of initialize with that data set and move towards that. And I think that to accomplish the kind of generalization that we want, we do need broader data sets, and we can't afford to collect broader data sets in the loop of a reinforcement learning algorithm. For example, if we had to collect ImageNet every single time we wanted to run reinforcement learning, that just wouldn't at all be practical. We'd generalize if we could do that, but that's not at all practical. So we need to start moving to these settings where we have these like initial very large and broad data sets that we can learn from and use to initialize our reinforcement learning algorithms. And without that, I don't think we're going to really see any generalization or any meaningful generalization from the algorithms that we're using. Some existing benchmarks that I'm aware of that I think are starting to go in this direction is there's this D4RL datasets for deep data-driven reinforcement learning that has a few different domains, including kind of simple Majoko domains, but also Carla, which is an autonomous driving simulator, as well as a traffic simulator as well, and I think some others. There's also a benchmark that DeepMind put out, I think last week, called RL Unplugged, that is somewhat similar in flavor, is also looking at this batch RL setting. And in the context of robotics, we've also started to put out data sets as well, data sets that of robots interacting with objects. We also we put out a data set actually of multiple different robots interacting with multiple different in multiple different environments, interacting with many different objects. And that's in an effort to hopefully move towards a setting where we're actually sharing data across labs, across robots, like the rest of machine learning, essentially. And ideally, I think it'd be great if these benchmarks can also not just engage the reinforcement learning community, but also people outside of the reinforcement learning community. For example, some of the robotics benchmarks that we've put out, people have used in video prediction and evaluating video prediction models, which is essentially learning a model in reinforcement learning. And these are people that really aren't experts at all in reinforcement learning, and they've been able to help us make progress on the reinforcement learning problem by building better models.
Yeah, so I mean, agree completely on that. And I can't. There was actually about 10 years ago, or 10 or 15 years ago, there was a formal, sort of an organized reinforcement learning competition that sort of was trying to go towards being a benchmark of sorts. The challenge there is that we always found is that fixed data sets are challenging for reinforcement learning because it's all about decisions, and every decision you make takes you away from the data. You get away from the region of the decision space where the data was collected. And so in some sense, you need a full simulator to be able to evaluate generalization. But if you have a full simulator, you're, almost by definition, it's a toy domain, or you're not in the real world. And so, how do you make a benchmark for the real world? I also can't, resist putting on my my hat as the current president of the RoboCup Federation and say, the robot soccer in the RoboCup world is sort of designed, has always been sort of a benchmark in the sense of, you can take your full algorithms and pit them against other people's approaches. And it's just like Chelsea said, it's not all reinforcement learning people. It's some people doing reinforcement learning, and it's other people doing, other approaches. And, that's there've been some successes, but, it's not always that reinforcement learning, or even often that reinforcement learning takes the day in that kind of a setting yet. And so, I think that's looking for more environments like that, and looking for where RL really dominates, not just itself, but or a particular RL against other RL algorithms, but also other approaches can really maybe be that moment for the community. I think we're almost out of time. Let me just give everybody an opportunity to make a final 30-second or so statement if there's anything you feel like you wanted to get across that you haven't yet. Let's go Jason and Chelsea, and then Ed, and then we'll wrap up.
Cool. Yeah, thanks everyone for tuning in. Yeah, I mean, as I said kind of in the beginning, this is the most exciting field, in my opinion. I mean, this is the next kind of big wave. I think there's so much low-hanging fruit. There's just every single industry, every single software developer is anytime you write any piece of software, you have an audience in mind. And so you're ultimately making decisions trying to improve that person's life, right? That audience, the lives of the people in that audience, right? And so, I think this technology will kind of move people more to focusing on the economics and the philosophy of whatever they're doing, which translates to better products and And yeah, I think it's an amazing space. I'm really glad people here are excited about it. And yeah, I'd love to see, you know, where it goes. I wish I had a crystal ball and could see what happens in 5 years.
Great. Yeah, I also think it's a really exciting, we're kind of in an exciting place in reinforcement learning where things are starting to work in simple problems, and hopefully we'll start to work in more challenging problems. One thing we didn't really touch on much in this conversation that I'd like to kind of iterate as a really huge challenge is the challenge of reward functions. I think we really need to be thinking hard about what the reward functions are, where they come from, the process of designing reward functions. And I think that these will become increasingly important as we actually deploy reinforcement learning systems that are interacting with users. And with any machine learning application that's actually deployed in the real world, we also need to think about kind of the ethics and the actual impact of these systems on society more broadly. And so I hope to also see, as the field matures, also more work kind of at the intersection of fairness and ethics and transparency and so forth, and reinforcement learning, as we start to trust these systems more with our society, essentially.
I love Chelsea's point just now about thinking about the fairness issues, particularly as we apply these RL algorithms in recommenders, for example. Those are first and foremost often in our minds. And indeed, we're actually working quite a bit looking at reward function design so that we end up with good outcomes from a fairness perspective. And so those intersections are very exciting areas for us to explore. I should say that RL turns out to be actually one of the biggest contributors to recent progress in recommenders. And so I do think that there's a lot of exciting new work that will come out in the next couple of years in this space.
Great. Well, that's a really good sign for a successful panel if in the last 2 minutes, some new topics come up that could lead to another hour of discussion, but we don't have time. So thanks to Ed, Chelsea, and Jason for making it really easy on me as moderator with all your great contributions. And thanks to Li Hong and all the organizers of the workshop for inviting the four of us to this panel. And thanks everybody for watching.
And thank you, Peter, for moderating.
My pleasure.
Yeah, thanks a lot.
So back to you, Li Hong.
All right, thanks, Peter, and thanks to all the speakers on the panel. This is really great, and I've learned a lot, and hope everyone enjoyed the conversations. This is, I think, we're running out of time, and this is the end of this panel session. We'll have 2 hours for the poster discussions, and if people interested in the posters can find the corresponding links on the website. And then, okay, I think that's the end of the session, and thanks again to everyone.
Bye.
Bye.